two parallel conducting rails, this top one and this bottom one, separated by 2 meters, are connected through a 3 ohm resistor, and a uniform magnetic field of 2 Tesla points into the page, and a conducting bar of mass 4 kilograms can slide without friction across the rails. So in part A, determine the speed and direction the bar must be moved to induce a counterclockwise current of 2 amps shown in the figure. So we have a current going around this circuit counterclockwise. So since we know the current and the resistance, we can go ahead and solve for the EMF that was induced using Ohm's law. So that's a current of 2 amps times a resistance of 3 ohms. So there was 6 volts induced. And now we can use the motional EMF equation. EMF is equal to BLV. Rearrange that for V. So V is equal to the EMF induced divided by the magnetic field times the length, or the distance between the two parallel wires. So that's 6 divided by the magnetic field of 2 Tesla times the length, which is also 2, that's 2 meters, and that's equal to a speed of 1.5 meters per second. So the bar has to move at a speed of 1.5 meters per second, but does that bar have to move to the left or to the right? Since the induced current is given as being counterclockwise, this means that the induced magnetic field must have been, using the first right-hand rule, out of the page. Because your thumb points in the direction of the current, so your fingers are pointing out of the page. Since the induced current is in the opposite, since the induced magnetic field is in the opposite direction, because the magnetic field in the figure is into the page, but the induced magnetic field is out of the page, that means that the magnetic flux must be increasing, because that's when the magnetic field is induced in the opposite direction. So the magnetic flux must be increasing. So the only way to increase the magnetic flux is if the area is getting bigger, which means that the conducting bar, to increase the area, must be moving to the right. For part B, determine the magnitude and direction of the external force that must be applied to keep the bar moving at that velocity. So, going to the second right-hand rule, you can see that if you put your fingers in the direction of the current in the bar, which is going upward, since the whole thing is going counterclockwise, put your fingers pointing upward and curl them in the direction of the magnetic field, which is into the page, you see your thumb is pointing to the left. But we want the bar to be moving to the right, so we have to apply a force to keep the bar moving to the right that has to counteract the magnetic force to keep it moving at a constant velocity. So the magnetic force is equal to ILB sine of theta. We can leave off the sine of theta since everything's perpendicular. The current was 2 amps. The length is 2 meters. The magnetic field is 2 Tesla. So the force, the magnetic force that the bar is experiencing is 8 newtons, which means that's also how much force you're going to have to apply to get the bar to move to the right. This is Newton's first law, where it's moving at a constant velocity, so the forces just have to be equal. In part C, determine the electric power, which is the rate that heat is being produced in the resistor. So the P is equal to, and there's 3 equations for it, IV, I squared R, and V squared over R. I'll use I squared R here, because the current was given as 2 amps, so that's 2 squared times the resistance of 3 ohms, which is equal to 12 watts. For part D, the mechanical power being supplied to the bar, mechanical power was expressed 2 different ways. We had work over time, or energy over time. We also had an equation for force, times velocity. And in this case, we know what the force is because we solved for that in part B, and we know what the velocity is because we solved for that in part A. So we can use F times V, that's 8 times 1.5, and that gives you a power of 12 watts. So you can see the answer to part C and D match because of conservation of energy. The power you supply to the bar is the same as the power that's being dissipated by the resistor. And then in part E, suppose the external force is suddenly removed from the bar. That means the bar is going to slowly come to a stop. Determine the energy dissipated in the resistor before the bar comes to rest. Well, all of the energy in the bar is going to end up being dissipated by the resistor, and since the bar is moving, that is kinetic energy. So it's basically just asking you to calculate the kinetic energy of the bar, for which the formula is 1/2 mv squared. So 1/2 times the mass of the bar, which was 4, times its velocity, 1.5, squared, is equal to 4.5 joules.